Okay, so revisiting the notes from Monday, after I made this video, and I don't know why it looks weird right now. After I made this video, I went downstairs and told my husband it's probably the worst lesson video I've ever recorded in my life. I couldn't form words. I think you'll figure that out if you actually listened to it and watched it. But hopefully I got the idea across, because it was pretty much a review from logs anyway, from Algebra 2. But I skipped the calculator part because I was doing it on my iPad and I just didn't have the strength to go through trying to record on two different things and putting them together. I'm pretty sure, again, since they're not brand new, you pushing the buttons on a calculator is not that big of a deal, except that these calculators are new for most of you, and so there's a couple of things that I wanted to talk about. So if you look at the back of the first piece of paper of your notes, find example 5. This was the first thing that we skipped. So this says to evaluate these common logarithms with a calculator. So what makes a common log a common log? The base. What's the base going to be? 10. Okay, good. So we're going to do this. So even though we don't see log base 10, it means log base 10 when you don't see one, of 34.5. So on your calculator, let's turn them on. And when we turn them on, get to the black screen, 1 for new. No, we don't want to save. And all we need is a calculator right now. We're not going to graph anything. So on every other calculator I have ever used, besides this one, when you push the log button, which for this calculator, it is to the left of the 1 and it's in blue. So, oops, that's not what I meant to do. I was just trying to point to it. It is under the 10 to the x. So if I do control log on every other calculator that, like I said, I've ever used, or probably that you've ever used, even if you didn't realize it, when you hit the actual log button that's easy to get to, it is the common log and only the common log. You don't even have an option to put a base in there, but this one does give you the option immediately, which makes it better for when you have to do the other logs. Usually that log key is hard to get to in the calculator, so this is kind of nice. But we know even though on our paper it doesn't say a base, we have log base 10, then we type in that 34.5, and we hit enter. So the log base 10 of 34.5 is 1.5378 blah, 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 which means that 10 to this power gives you 34.5, right? That's another way to look at it. So let's write that down. This is 1.5378. So another thing about this, though, since this button usually does just give you log base 10, if I get here and I don't fill in the base of the log, and we do the next one, which is 0.43, 0.43, it fills it in for me and makes it 10. So you can leave it, if you know it's 10, you can leave it blank and it'll just take care of it and make it 10 for you. So your log base 10 of 0.43 is negative 0.3665. Okay, easy enough? All right, so then let's do log of negative 3. So log base 10 of negative 3. Type that one in. And instead of just getting a syntax error or something like that, which sometimes means you don't have enough parentheses or something doesn't make any sense, this is telling you it's not that it doesn't make any sense, it's just that you're going to have a non-real calculation. Does that mean you did something wrong? No. That just means that this answer does not exist. Okay? And let's talk about why. So it says on D, using your answer to example 3C, which it's not example 3C, it's C from this right here. We can see that we can take the log and we can get a positive answer, we can get a negative answer, but look what happened when we took the log of a negative number, right? It didn't work out. So is that true for all negative numbers? Let's see what happens here. If I let log of negative 3 equal x, and I rewrote it as an exponential, my base is 10, so 10 to the x power equals negative 3. Is there an exponent that exists that I can take 10 to that will give me a negative answer? No, there's not, and that's why the answer doesn't exist. That's why you can't take the log of negative numbers, because that would be your answer basically from the exponential, and it's just not going to work out for you. Okay? So one thing that is important to know is that if we have y equals the log of x and we were going to graph it, it looks like this. Okay? We would have this right here, and we have an asymptote here at x equals 0. This right here is 1. Because if this is the parent function, the log base, whatever, the base doesn't matter. The log of 1 is 0 every time. Knowing what this parent function looks like can help you. Okay, in calculus, we don't use logs like this. We use natural logs, which we'll look at those too. But the natural log, the graph looks the same. And having that picture of the parent function in your mind can help you with domain and range and what values you're allowed to use and things like that. And to help you remember that the log of 1 is 0 no matter what the base is. If you know what the graph looks like, that's what's happening there. And if my x is negative 3, it's way out there, so you can see why this doesn't exist. It's not in the, negative 3 is not in the domain. I can only go from 0 to infinity. Okay, everybody okay with that? All right, so then next sheet of paper on the front, I think. Yeah, it's right here. So now we're taking the log again, but it's not the common log this time, so we have different bases. So log base 3 of 15. I would do log base 3 of 15. This time you have to put the base in or it's going to default to 10 and get your answer, which is 2.4649. And go ahead and type in the other 3. We get 2.4649. And go ahead and find the other 3. I'm going to write them up here, but I don't want you just copying mine. I want you pushing the buttons, making sure you can push the buttons correctly. Anybody having any trouble getting any of those? All right. Are we good? Can we move on? All right, so before we do the last part, I'm going to show you a quick little video that ideally, I would have showed you on Monday, but I wasn't prepared for all that. So this is a quick little 3-minute video about logs.
How does the difference between 0.00000000398 and 0.00000000398 cause one to have red eyes after swimming? To answer this, we first need a way of dealing with rather small numbers, or in some cases extremely large numbers. This leads us to the concept of logarithms. Well, what are logarithms? Let's take the base number b and raise it to a power p, like 2 to the 3rd power, and have it equal a number n. We get an exponential equation, b raised to the p power equals n. In our example, that'd be 2 raised to the 3rd power equals 8. The exponent p is said to be the logarithm of the number n. Most of the time, this will be written log base b of the number equals p to the power. This is starting to sound a bit confusing with all the variables. So let's show this with an example. What is the value of log base 10 of 10,000? The same question could be asked using exponents. 10 raised to what power is 10,000? Well, 10 to the 4th is 10,000. So log base 10 of 10,000 must equal 4. This example can also be completed very simply on a scientific calculator. Log base 10 is used so frequently in the sciences that it has the honor of having its own button on most calculators.
But not ours.
If the calculator will figure out logs for me, why study them? Just a quick reminder, the log button only computes logarithms of base 10. What if you want to go into computer science and need to understand base 2? So what is log base 2 of 64? In other words, 2 raised to what power is 64? Well, use your fingers. 2, 4, 8, 16, 32, 64. So log base 2 of 64 must equal 6. So what does this have to do with my eyes turning red in some swimming pools and not others? Well, it leads us into an interesting use of logarithms in chemistry, finding the pH of water samples. pH tells us how acidic or basic a sample is and can be calculated with the formula pH equals negative log base 10 of the hydrogen ion concentration, or H+. We can find the pH of water samples with hydrogen ion concentration of 0.00000000398 and 0.00000000398. Quickly on a calculator, punch negative log of each of those numbers, and you'll see the pHs are 7.4 and 8.4. Since the tears in our eyes have a pH of about 7.4, the H+ concentration of 0.70398 will feel nice on your eyes, but the pH of 8.4 will make you feel itchy and red. It's easy to remember logarithms. Log base b of some number n equals p by repeating the base raised to what power equals the number. The base raised to what power equals the number. The base raised to what power equals the number. So now we know logarithms are very powerful when dealing with extremely small or large numbers. Logarithms can even be used instead of eye drops after swimming.
Okay, so his speech pattern is a bit on the annoying side, but one of the things that we're going to look at in this next example is kind of what he's getting at here. That these two numbers are very, very close to each other, right? And when we're looking at, like on a graph, it would be hard to even distinguish maybe the difference between the two. But the difference between 7.4 and 8.4 is much easier to distinguish. They're much farther apart, depending on what your scale is and what's happening, and would make more sense. That's why we talk about pH like this instead of with all the billions of zeros there. All right, so let's look at the back of the second piece of paper here. So this part I'm pretty sure I skipped altogether. So one useful purpose for logarithms is dealing with exponential data. Okay, exponential data can be very challenging to display graphically because the values may start out very small, but they grow quickly. That's the concept of an exponential, right? Something growing exponentially grows very quickly. So it's difficult to create a display that effectively shows smaller values along with extremely large values. So if you look at this graph here, so this data represents the population of English Americans in the current United States. Oh my gosh. Since 1620 has grown exponentially. And so this is the estimated population from 1620 to 1820, so 200 years from when 1620 was, right? So here shows the population using a normal scale, just based on what the population actually is. And because it extends into the millions, if you look early on, these early years, you cannot even tell much of a difference between those, right? Because we had to use such a big scale because these numbers get so big that kind of gets lost and looks like there was hardly any change at all. But there was a good amount of change. So this graph on the right uses a logarithmic scale with a base 10 for the vertical axis instead of the actual population. It's the log of the populations, so that you can see early on that things did kind of change pretty well. And here there was like kind of a big jump, which you can't tell that happened at all over here. All right, so this, and I think my jacket is writing on the board as well. Now this graph right here, this goes to 200 years, and so did this, but then I extended it some more because we are going to plot the next 3 years, the 1840, 1860, 1880. And you can see that there was a little over in 7 million right there, and then we jumped to 17 million, then 31 million, then 50 million. So we're going to make another, we're going to go ahead and do this so you know how much room you have to write other stuff, because we're going to write something down before we do anything else. So notice up here, because this goes to 10 to the 7th, right, I'm not going to plot 17 million. And on here, if I had to plot 17 million on the left graph, I'd go way off my graph, right? Especially even to get to 50 here. So what we're going to do is we're going to take the log of 17,069,453. Okay. So find the log of that on your calculator. get 7.2322. Okay? If you're like, that's great, but I don't really know, still not sure what all the heck that means, right? Well, if I rewrite this as an exponential, remember my base is 10. This means that 10 to the 7.2322 power equals that 17,069,453. So when you look at your scale on the right-hand side over here, we had 10 to the first, second, third, all the way up to 10 to the seventh. So this is a little bit more than 10 to the seventh, right? Which makes sense. I can actually graph it on here where I can't even graph it on this one right here. So what we're going to find in here, this is going to be the log of the population. So we found the log of 17 million. It was 7.2322. Go ahead and find the log of the next two values. And our log values way closer together than our actual population values, right? Which were hugely far apart. So by taking the log of all of them, it has done two things for us. It has taken this first part of the data that was squished together and separated it out some. Then it took the other part of the data, which was spread out, and kind of squished it together where we're all on this same kind of grid where we can see what's actually happening there. So we want to plot these points here. This is 10 to the 7th, so I'd say 10 to the 8th is probably right about there. So for 220 years after, which would be 1840, we'd be at 10.7 something. It was a pretty good jump. And then a little bit more, and then something like that. It's probably not great, but you have three other points up there. That's the idea, is that they're not too far apart. Okay. We good with that? What questions you got? Okay. Did you have questions on any of the rest of the notes? Something you felt like I said and it really made absolutely no sense, or anything? Like you were good? You could figure that stuff out? All right, I'll take that as a yes.